Hi, everyone. Thank you for joining today's session. It's already recording. Okay. Excuse me. Thank you, everyone, for joining today's session. Today, we're going to start a series of free training sessions just to get you all into Karamba. And so this is going to be in a sort of 30-minute format. During the session, I won't be addressing questions live, but feel free to try to ask some questions in the chat if anyone might have. I'm going to share where the example that you can find that we'll be going through in today's session right now here, but you will also see in the small presentation that we are sharing shortly. And Sarah will be here to assist if there's any issues as well. So we're going to kick off now with a short introduction. So like I said, this is going to be a first introduction to beams, and we're going to have a couple more sessions coming up soon. Just a quick sort of update for those of you who have not used Karamba much or have not looked at our examples that are available on our website. What we generally have done on our examples is that we've grouped them according to different types of colors, and the group colors correspond to different types of applications. And these are all standardized amongst all of the examples that we share. In this sort of dark gray, dark blue-ish color, this group always relates to, this color always relates to any geometry applications that might be referencing geometry from Rhino, for example, or actually creating geometry parametrically in Grasshopper. And so this is always grouped as a start as a sort of dark gray color. Next, once we have our geometry, let's say, created or referenced into Grasshopper, then you always start converting them into Karamba, let's say, model entities. So these entities are the elements, which are shells or beams. Then you have cross sections, so you can define different cross section properties, material properties, the support conditions, and the loads. Of course, there's additional ones that you might want to also define, such as joints or element sets, but the basic list is explained in this slide. Next, once you've got all your model entities assembled in a model, we take the model and run a calculation. So these calculations are also grouped according to different types of algorithms that are available in Karamba. So it might be analysis in the first or second order theory. It might be an optimization of the cross sections. You might be wanting to do a form finding with large deformation, or if you want to do a buckling modes analysis as well, for example. And lastly, those components which relate to extracting or previewing results are grouped in the red color. So this is the model view, the beam view, shell views, and any of the results components such as utilization or reaction forces. So just to give a brief overview, we always have this geometry input, as I mentioned. Then the geometry is converted into a beam. In this case, a line to beam. You define cross sections, you define material, supports, loads, and you assemble it all together as one model. Then you can run the analysis on your model and extract the results using the model view and the beam view in this case. So for today's example, I've shared the link in the chat, but you can also download the reference file that we'll be looking at today. It's a small example of a 2D sort of warehouse frame, looking at how you can define cross sections, supports, joint conditions, and loads, for example, and also extract results and visualize them in Karamba. So this is just a quick preview. As I explained already, we group them according to the color. So you can see most of our scripts are always going to be arranged like this, so that it's clear for you to understand which parts are coming from which specific components. So with that, we'll jump into the live script. So I've opened up now my grasshopper definition, sorry. And so here, when you open up the definition, you will always see a store heading that explains, for example, a small text, what necessary plugins I might need in the component for the grasshopper definition. And as I mentioned, the different colors or components grouped in the different colors, as you can see. Just a quick sort of intro to the Karamba sort of, let's say, dashboard in a way, or the menu. We have the settings that you can control here in the actual menu up here. So for example, if you wanted to set the language, change the user settings, if you wanted to turn off different components, the VIP, the work in progress, or parametric UI, or if you wanted to change the units. And generally, all of the components in the Karamba tab are arranged in sort of order of how you specifically would use them. So the license, of course, the parameters which allow you just to collect different data, and then the subsequent model load, cross-section, joints, and materials. Then we have the algorithms, so the different calculations that you can run, results, and then the last ones are the export and utilities functions. So let's now look quickly into the geometric function of this script. So it's a very, very simple script where we're just creating, let's say, a 2D frame, sort of with sort of 2 columns and then 2 roof beams with a pitched roof here. We can use these sliders to control the width of our frame, the height of the column, as well as the pitch height, for example. And as you can see, everything has been connected to Karamba. So as you change these parameters, it will update the calculation live as well. Essentially, what we're doing is going through a different, we're taking a starting point and moving these points to basically draw this frame parametrically. But of course, this could be referenced in using simple reference geometry in Grasshopper or drawn in Rhino, for example. So in the end, we start with a polyline, which has been joined, and then we explode it to create the subsequent separate line segments. Now that we have separate line segments, we basically convert these lines into a beam element using the create linear element component. We can specify if you want to create a beam or a truss. In this case, I'm currently wanting to create a beam. So it has bending stiffness. And we are giving some IDs, in a way, names to those 4 elements, A, B, C, D. And this relates to the order of our lines in the list as well. Next, I'm using the cross-section selector to select a standard cross-section from the Karamba library. You can, for example, here just use a panel and input a different text if you wanted to change the cross-section, for example, by saying 600. And then you can see that the cross-section here has now changed to suit this cross-section. In 3D, you can see that the cross-section is a bit more better shown. I'm using the, this one is somehow not plugged in, but the material selection component allows you to select material by country. You can filter by country now, and the type of material as well as the material grade. In this case, we're using a standard 235 grade steel. For the supports, we have the 2 points of our columns as support points, and we're applying different conditions to the supports. So sometimes it's a bit harder to see, so I'm going to turn off my preview of the beam view by clicking on the object and doing disable preview. And so you can see the support conditions a bit clearer in our Rhino viewport. So on the left, we have, which is this one, we have the TX, TY, TZ and the Rx, Ry activated. And if we start to release or basically select these, activate these conditions, you will see that the arrows disappear or the circles disappear or appear accordingly to that condition here. And of course, this would affect the results in your calculation as well. So if you were to, for example, change it, you will see how the bending moment diagram also changes as you release or add a specific condition to your structural model. For the loads, here we have applied a few different load cases. So first, we're using the loads gravity, standard gravity. If we're using gravity on Earth, we don't need to apply a direction of gravity. We just use the standard 0, 0, -1. And I'm giving a name to this load case, calling it gravity here. For the next component, we have a line load. And in this case, we want to apply a uniformly distributed line load on our roof, which you can see are these line loads there. So in this case, I've selected that beam ID B and C should receive the load. The load case is roof in this case. And I have a force vector of 10 kilonewtons, negative X. But I've applied this local to the element. So that's why you can see that the load is actually applied oriented in the Z direction of our actual beam. If I was to apply global, for example, you'll see that the load gets oriented globally to the X, Y, Z axis, and global projected will also adapt this according to the geometry and the position of your load, similar to snow loads, for example. So I'm going to keep it back to local to element. The next one, we're applying a wind load. In this case, the wind load is on our columns, and we're applying it globally in the horizontal direction. So that's why I have, for the force, an X direction, and I've set the vector to be, the orientation to be global. And my load case for this one is wind. So if I want to now see the load applied onto a model, we can go to the model view and look at the result selection. At the moment, roof has been activated, but I want to look at wind. And so let's maybe also turn off the preview for the beam view. And here you can see that the wind load has been applied. Actually, sorry, I wanted to apply it on this side of let's say our building. And so that's why A and B has been defined there. And you can see load has been applied globally in the X direction on our column and our roof beam there. If you want to also see the load value, you can go to the annotations and turn this on as such as well. So that's our beam load in the wind load case. And lastly, we want to use the load case combinator to apply a load combination. So a load combination is simply a simple equation where first you write the name of your load combination. So in this case, my name is ULS, ultimate limit state. And then you write equals. And now we start to apply the different multiplication factors as well as the load cases that you are considering for that load combination. In this case, we want to basically multiply the the gravity and roof load by 1.35, and then we're adding the wind, as you can see. And there are many different ways you can apply different types of very intelligent load combinations using these type of, let's say, standardized methods of adding or subtracting load cases. Check our menu for more information about this as well. And so once we have created that, you see that now we have a ULS load combination. And then that has been converted into a load for Karamba. And to visualize this, we can now go to the ULS, and now you will see that we have gravity, which is the red arrow down, 1.35 multiplication factor. We have the wind load, which has been applied as a 100% factor, 1.6, and then the roof load has been multiplied also by 1.35%. Oh, 135%, sorry. That's why you see 13.5 kilonewtons per meter for the roof. So lastly, in this combination, definition, we have a couple of components that can help us define different joint conditions. In this one, we're using the beam joint agent, but there's also the beam joint component that allows you to apply joints to all beams that have a specific ID. But the beam joint agent is quite useful because you can actually specify the connectivity. So in this case, we want to say that the B beam, for example, the second one here, has a joint condition when it connects to C, which is this one. So essentially at the pitch, we have a release. And this release is the Ry, and that's why you see this circle there. If you were to say, for example, at A, you can specify it by writing A, and you'll see that the joint is there. So it would only, and if you were to write, for example, D, B does not actually connect to D. If I actually go to the element tags, we can see our actual element names. I should have done that before, but here you can see B element doesn't connect to D, so that's why there's no joint being applied here. So you can use it quite intelligently to give, let's say, a rule-based system for your joint conditions here. And for example, if you then want to release it also in the TZ, for example, you'll see that it's now released, and you can, of course, it will then affect, of course, the calculation model as well. So now I've released it there. We can have a look. What does this mean for our model actually? And so here you can see that once we've released the Z and the TY, we have a very, very different result there. This is the ULS load case. And if I was to now make everything rigid again, this is how our structure now is performing in the ULS load case. Let's turn back the RY release on. And if you wanted to apply a spring stiffness, you can simply put a vector here. And so a vector could be a number. So for example, if we're saying RY, we can say 0, 10, 0, and that will apply a certain spring stiffness to our release as well. So we have everything in our model now assembled, and you've already seen what happens when we start changing parts of our all the different entities. Once you've assembled the model, you always get a total mass of the model as an output. There are also some information about the center of gravity of the model. You can also extract all of the load case names from that model as well. Next, we are using the analysis as a default, it's the analysis in the first order theory. And as a default, it also analyzes or calculates for every load case or load combination in your model. But if you only want to actually calculate ULS, for example, you can do so and plug that in as the input there. And now we only calculate for that specific load case or load combination. And that's why here you actually see 4 results, because there are 4 different load cases or combinations in our model. If you hover over a input or output, usually you can see the units. And so here, for example, this shows us the maximum displacement of the load case for each load case. And of course, this corresponds to the order that you have here, LC names. In this case, here we have it in centimeters. Here you can also see the resulting force of external loads, as well as the change of elastic energy as an output as well. So the last part of the script is showing you how to then view the results in your model. So we first take the model view, and the model view basically is the axis model that we have inputted. It has no, let's say, geometric information of the cross sections shown in the model view component. So we see the geometric axis here. We can turn on and off the deformations as a standard. And then we just, here we have the gravity load case, but here we can pick different load cases if you want to visualize it. There, the deformation is quite low, so we can also double click. And if you double click on the button, you can actually change the slider value. So if you need to make it larger, you can set it so you can exaggerate the deformation shape even more. For reactions, you can turn on the reaction forces here and scale also them up and down. Sometimes if it's hard to see it in the Rhino viewport, I would suggest you to use the grid component and turn off your grids and the world axis here so that you don't see those in your Rhino viewport. And so you can see the reaction forces for that load case or load combination. Here we can turn off the preview of the support conditions. If we wanted to look at the local axis, and this is very important when we're working with, for example, beam loads on which apply locally to the element. When we go back to the load case with roof, and we turn on the loads again, you will see that for each element, we always have a three lines for our local axis. There's a red, green, and blue, where red corresponds to the x-axis, and x-axis is always the same axis as your beam element. Then we have the y, which is the green one, and then the blue one, which is the z-axis. And so that's why here you can see that local to axis for the beam load is now in the same direction as our z-axis there. So it corresponds to the local axis there. Let me turn that one now off. And joints are then, of course, this joint that you see now there. If you are working with, for example, truss elements, you will always have orange let's say, dots at the ends of your beams. When we go to the render settings, this allows us to control actually settings for the model view and the shell view. And so maybe now what I'll do is turn this on. And if I go and actually turn on my mesh edges by going to display and preview mesh edges, we can actually see a bit clearer what's actually happening here. So length segment controls how many divisions are shown in the render preview. So if I set it to a much higher number, you'll see that the division of my beams gets much lower. And if I set the number to be much smaller, you'll see that I get more divisions on my mesh, which also means that the curvature of my, in this case, the section force of the bending moment is also smoother there, which we have more divisions. This has no effect on our results, it's only on the visualization. And of course, this also has an effect on how the object actually deforms. So you might sometimes think, why is my deformation shape so rigid? If you go to the length segment, you can actually adjust this to make it smoother. The upper and lower threshold allows us to control the upper bounds and the lower bounds of our legend, or basically of the results here. So you can see by changing the percentage there, you can actually set the lower bounds and upper bounds and see where actually we're meeting a minimum threshold or a lower threshold by this color, the yellow or the green, for example. Lastly, we had a look already at the annotations, but you can turn off different components and to see the cross-section names and material names, for example, the actual element number as well. And lastly, if you wanted to color the elements according to, in this case, we haven't actually colored anything, so it's not going to give us any different results. And lastly, to sum up, we're going to just go quickly into the beam view, where we have the section forces tab. So firstly, here you can see I have bending moments activated, and I can turn on the numerical values in the preview as well. And I can actually scale the render of our bending moment. If we wanted to look at the axial forces, so NX, we can turn on NX here. And of course, this is relating to that specific load case or load combination. And here, this relates to the scaling of your shear or normal forces. Lastly, in the render settings, we have the option to just see the cross-section, which has no values, just the color. We have the axial stresses. We have a stress-strength ratio, which of course will adapt according to the cross-section and your loads that you apply. And then we have the displacement settings. And lastly, this component allows us to add more resolution in the cross-section of our element. So for an I-beam or rectangular cross-section doesn't really have much effect, but for a pipe, this would make it much more smoother in the rendering. And now you can actually go in and bake your model also into Rhino. Here I have it on shader view now, so you can actually see that the colors are also baked into Rhino as well for this preview. So you can make some nice images or save it as a state of your model. So I think time is up now, but this was a very quick introduction to how you can get your first introduction into Karamba. I just want to show one final slide where I just want to show that we have a second training session coming up in 1 month, where we'll be doing a sort of introduction into shells. So a similar approach, half an hour, going through a prepared example to guide you in the first steps of how to use Karamba when we're working with shells. Thank you everyone for joining this session. We will be posting this recording on our website and YouTube and Vimeo platforms later on. So you can also watch this, as well as the script is also shared already, but we will also be sharing it on our website for everyone. Feel free to ask questions on a forum if you have any questions, or on our YouTube channel, and we'll try our best to answer them as much as possible. And we're excited for everyone to have joined us today, and hope to see you all next time for our next session.